Okay. Okay, ada lagi. Okay, so okay, I ask someone first a theoretical question. Okay, okay, Eugene, are you there?
Yes.
Can you name to me the four basic component device in a gas turbine cycle? The four basic component. What are they in a gas turbine cycle? What do you need? Can you name me the component? The four basic one without regenerator, intercooling, reheat, etc. What are the four basic component in a gas turbine cycle? Can we name at least a few, Eugene?
Condenser.
Condenser, okay. So that is a closed cycle. Okay, if you have condenser, means that is a closed cycle. Okay. Another three.
Compressor.
Compressor,
Expansion device.
expansion device or turbine. Okay, for expansion.
Dengan evaporator.
Evaporator or boiler or combustion chamber for jet engine, right? Okay, thank you. Okay, so actually you have several options, okay, to answer, of course. Okay, but the main process is only four. Okay, those four. So normally we will start with for closed cycle gas turbine. Closed cycle means for power plant, for industry power plant to produce electrical power, mechanical power. We use closed cycle. Okay, so closed cycle, at least we start with pump or compressor to compress. Okay, I repeat again. So I draw and okay, you can look at the whiteboard also. Sekejap, okay, so the four basic, we have compressor. Actually, compressor. Okay, wait. Ni lah. Okay, compressor normally we the schematic diagram for compressor is like this. Okay, from higher pressure to lower pressure. Compressor or pump, okay? Compressor or pump. So compressor for air or gas and pump is for liquid. But the function is the same, to compress to a higher pressure and temperature. This is for liquid. Okay, so you have compressor first and then you have something to increase the temperature, increase the pressure, to evaporates, to boil. So you use boiler, okay, to exchange the function, to boil and to exchange the heat with the heat source. So you have boiler, we use the boiler for liquid. For air, gas, vapor, we use evaporator. Okay, and for jet engine, this one is replaced with combustion chamber. Okay, combustion chamber for jet engine, this function at this point is replaced with combustion chamber. So you have to understand this. The different component depends on the function lah. Depends on the working fluid. So combustion chamber, this one is for aircraft engine or jet engine. Jet engine open cycle. Okay. Okay, so mainly this part is where other than to increase temperature and pressure is where the component, the device, evaporator, boiler, combustion chamber, where it change heat. So that's why it is called heat exchanger, types of heat exchanger. These three are types of heat exchanger. Okay, means that these three component will exchange heat with another fluid or another fluid to so that it can evaporate, so that it can boil, okay, so that it can increase temperature. So for example, combustion chamber, the heat source will be fuel. Okay, so fuel and oxygen. Okay, so the combustion process will occur. Evaporator, Depends. Evaporator boiler depends. If the heat source is a natural gas or conventional use natural gas. So this is the heat source lah. Okay, so it will exchange heat with the natural gas. Or sometimes if you use renewable energy, so the heat source will be solar PV, solar power, solar system. Okay, so if we change the working fluid inside, for example, water, the working fluid running from the compressor to the boiler. So the water will exchange heat with the, for example, solar. Okay, so solar has a higher degree of temperature. So it's kind of like it will evacuate the heat to transfer its heat to the water inside the boiler, and the water will increase and solar PV will cool down a bit the temperature. Okay, so that is why heat exchange. Heat exchange between the working fluid inside water, gas, the main working fluid in our cycle with the heat source outside. Heat source, right? So this part is the heat source that we call heat source, heat sink kan, for the heat engine. So this part will have heat source outside, from the outside. Okay. And then we have, okay, Eugene mentioned just now, expansion device. So something to expand. Okay, so usually we will use turbine. Okay, a turbine to expand to expand, to decrease the pressure and temperature of the working fluid inside. Turbine, expansion valve. Okay, so that is the function. Okay, and usually this turbine for closed cycle, it will be connected with a generator. Okay, to produce electricity. Okay, mechanical power, etc. Okay, because this is where the net power output, the electricity, the main our required output is produced. Okay, here. Okay, turbine or expansion valve, etc. Okay, so and then for closed cycle, you have another heat exchanger, which is we call it as condensation process. Okay, so of course when you after you evaporate, you have to condense back to complete the cycle. Condenser. Okay, normally we will use a condenser lah. Okay, so condenser like this one, it needs we need a heat source to evaporate or to boil our working fluid inside, our water or gas inside, right? So for condenser, the function must be the opposite. Okay, means to cool down. We need to cool down back, so we have to condense it. So we need another reservoir that we call heat sink. Okay, this is the reservoir for heat source, natural gas, solar PV, or any boiling water. Okay, that is the reservoir for heat source. For cooling, okay, to cool down the temperature of the working fluid, to condense it. Okay, so we need another thermal reservoir that we call as heat sink. Okay, the term used is heat sink. So normally this heat sink is it can be our environment. Okay, our ambient environment is the heat sink. Okay, so when the our working fluid or air or gas coming out from the turbine, it is at a higher temperature after exiting the turbine. Of course, because it has produced power, etc. So it is at higher pressure and temperature exiting the turbine. So in order to cool down, to condense, so it need to exchange heat with something, okay, which is with a heat sink, okay, to exchange heat with something so that it can cool down the pressure and temperature. So we need something like our environment, ambient air, or usually for power plant they use cooling water. Okay, something to cool down. So cooling water. Okay, so that's why we have like a cooling water tank beside the power plant to cool down, to condense. Okay, so the working fluid inside, the hot temperature, we exchange it with the cool water outside here. For example, something like this. Okay, we will draw schematic diagram, something like this, to exchange heat with the cooling water. Okay, so after that, it cools down. So to complete back the cycle, we continue back, entering the pump, and the compression process will occur again. So like this. This is the basic. Okay. So for jet engine, our jet engine here. Okay. For jet engine, exceptionally, we don't have this part. Okay. We don't have this condensation part. After exiting the turbine, it will enter a nozzle. Okay. So that nozzle, so that the gas will be accelerated to a high speed gas flow velocity, okay, to produce, because we need thrust to produce kinetic energy, high kinetic energy thrust, okay, and then the waste heat, okay, after the nozzle will just rejected, okay, to the ambient environment, okay, and then to restart, okay, to do it again, the cycle, okay, the pump compressor will have an intake fan. Okay, the function of compressor and fan is the same. So that fan, it can and diffuser also. Sorry, diffuser. So we have this is I'm talking about jet engine. Okay, okay, don't get confused. I'm talking about jet engine. Okay, we have finished the power plant. So for jet engine, we have extra component, which is nozzle, to increase the gas. Okay, at high to high speed gas flow, so that we can produce thrust for the jet engine to propel for propulsion. Okay, so and then but we don't, for jet engine cycle, Brighton cycle, we don't have this condenser part. Okay, the air, the waste heat will be just rejected to the ambient environment. Okay, and then to start again the cycle, the air from the ambient will be at the intake. This is at the intake. You have another component before the compressor. We have diffuser. So the function of diffuser is the opposite of the nozzle. Okay, easy to remember. The function of compressor is the opposite of the turbine. The function of the diffuser opposite of the nozzle, and this one also opposite of each other. So diffuser is to decelerate. Okay, to decelerate, because we want to like capture the air from the ambient, so that it can enter the core engine here, compressor, okay, and for combustion process, etc. Okay, so to capture it, so the at the intake we have a diffuser to decelerate, okay, to decelerate, turunkan dia punya tu, okay, slow down, to slow down the speed of the air ambient at the intake, okay, to decelerate the kinetic energy. Okay, so that you can like capture the working fluid air, okay, and it can enter our core engine, which is starting from the compressor, boiler, etc. Fan is extra component if you if you use turbo fan. Okay, so this one you will learn in propulsion, next semester, inshallah. Okay, if you use turbo fan engine, you need extra fan, but the function is the same as compressor. Okay, enough. So this is just explanation of the basic gas cycle. So I have repeated this several times. I hope that you by now you have like tanam planted in your brain. Okay, so your head. So in the back to our questions. Okay, back to our exercise. Okay, steam enters and adiabatic turbine. So what we are talking about, what does this question talking about? It only focus on this part, turbine. Okay, the question just now, exercise 1, only focus on this turbine, this device, steam adiabatic turbine. Okay, so we're just focusing on this part. Okay, okay, continue to answer. I just want to refresh back your memory about the gas turbine cycle, and so you can answer. Okay, try to answer. Steam enters an adiabatic turbine steadily at 3 megapascal and 4 degrees Celsius. Okay, so means here 3 megapascal, 400 degrees Celsius, entering the turbine. I changed a lot of time. Okay, 3 megapascal. Okay, so here means at this state. Here, okay, entering the turbine. So here at this state, bukan kat sini, not here, not here, not here. Okay, this one here. 3 megapascal, 400 degrees Celsius. Leaves at 50 kilopascal and 100 degrees Celsius. So leaving the turbine 50 kilopascal, 50 kilopascal. So okay, means that we have expanded, we have decreased the temperature, pressure and temperature 100 degrees Celsius. Okay, usually when we decrease pressure, we will also decrease the temperature. It proportionally relates to each other, temperature and pressure. Okay, and then the turbine are able to produce power net output 2 megawatt. 2 megawatt, or if you want to write, it means that 2 megajoule per second. Okay, by now you have to know all the SI units, what is translated into joule per second. Okay. So the isentropic efficiency of the turbines. Okay, so we have to know the isentropic efficiency. Of course, the turbine is not ideal. Okay, the turbine not functioning at 100%. Okay, it has some energy loss. So we have to determine what is the efficiency of the turbine. Otherwise, maybe we have higher. We will not higher, lower pressure and temperature. So since that the turbine is not at 100% efficiency, so it has some sort of energy loss that it cannot expand to roughly 100% lah. Okay. Okay. Back to the okay. I want, before you answer the question, I want you to sketch the process of this expansion in the turbine in a TS diagram. Okay, I want to ask someone to sketch just the process. Okay, TS diagram, temperature versus entropy. How is the line, okay, of this process expansion in a turbine on the TS diagram. Okay, you can turn to on the whiteboard. You can turn to page 2. Okay, just turn to page 2. I want to ask. Okay, Mutaman. Mutaman.
Yes, doctor.
Okay, can you open the whiteboard, the online whiteboard, the link in the chat? Okay, try to sketch the process of this the process within the turbine, which is expansion, in a TS diagram.
I'm not good at drawing, doctor.
Sorry?
I'm not good at drawing.
No, it's okay. You don't have to draw beautifully or what. Just I want to see how the process, whether it increase or decrease, or whether it's a straight line or have a slope or etc. I will ask this some sort of questions in a final exam, so you have to at least try to think about it. I think we have done this several times. So how is the line, okay, in a TS diagram, the process?
One moment, please.
The whiteboard, yes. This is only this is just theory questions, not yet calculation, okay? You can use the page 2.
Trying opening the website, but it's only letting me to download
To download.
the second application.
Actually, you don't need to download. Just use Google. For others, try to get the parameters at the input. I will ask also somebody else after this. What is the enthalpy at the input, entropy, and the parameters at the exit of the turbine also. Find the enthalpy, entropy, okay? And we will use that to calculate, yeah. We will use that to calculate the turbine entropy.
Yes, miss. Now it actually downloaded. Sorry, miss. Would you want me to sketch again?
The process of the expansion in the turbine, exercise 1 in a TS diagram. You can use the second page of the whiteboard. Just click right.
Yeah, I know.
Ah,
So just the expansion process, miss?
yes. The TS diagram. Apa lagi ni? Zainul dengan Afiq, kita tengah buat sesuatu ni. Tadi saya spray panjang lah, nanti tengoklah link dekat whiteboard ni. Afiq and Zainul, you can open the whiteboard link because I will ask any one of you to answer exercise today. Okay, what is this? Okay. So your TS diagram, and okay, sekejap, saya tunjuk. Okay, so this is your TS TS diagram and the expansion process.
Totally not sure, miss. As far as I can remember.
Sorry. I cannot understand you.
Not
What?
sure of this. I'm not sure.
You're not sure. You don't know. You don't know anything about the expansion process.
Yes.
Okay. In expansion? Okay. When measure expansion, which parameter increasing or decreasing, in your opinion? When expansion, when we say expand, what does it mean by expand? Definition of expand.
To become bigger, no?
To become bigger. Okay. What is the parameter that will become bigger? One parameter. In thermodynamic, of course. Okay, you said that it is become bigger, but what? Which parameter is affected? Okay. Yeah, Taman, you can answer. Entropy, enthalpy, pressure, temperature, velocity, volume. What else you know in physics? Yeah, which parameter will increase? Okay, in theoretically we see it will become bigger, but the correct what is the temperature, the parameter that relates to this, mainly to this expansion process, the same as compression. So which parameter? I've explained it just now in the first page of the whiteboard. If you want to look back at the first page of the whiteboard, I explained 10 minutes, I think, on that. Yeah, Mutaman? You have any idea? You can look at the first slide, first drawing, which where is the turbine?
Pass, doctor.
Sorry?
Pass. I can't answer.
You don't know, okay, where, okay. In this, where is the turbine? Okay. Okay, of course. Okay, okay. Today, of course, this is not your exam or test or anything yet. So I want you guys to understand. So, until you answer me, okay, I will guide you to answer it correctly and you understand. Okay. So where is your turbine? That one, the purple one is you. Are you the purple icon there?
No, doctor, that's me.
Okay. So Tian Shan have give you some hint. Okay. So that is the turbine. Okay. That is the turbine. Okay. So which parameter is increasing or decreasing, whatever affected?
Because, doctor, honestly, I can't tell which one is the turbine from all these drawings.
Did you listen to me just now when I started
did.
the exercise?
Yes.
I've explained this one. I've explained this schematic diagram. Did you listen?
Yes, I did.
So where is the turbine? I've mentioned that this is the turbine. Even though if you do understand the drawing, if you know the cycle, compressor, boiler, the basic 4 cycles, so where is the turbine situated? Here. Okay, so the turbine. So which parameter affected when you say expansion just now? You wanted to draw, you wanted to sketch. Okay, so which parameter affected? When you said that expansion, it will get bigger. Okay, somehow, okay, that is correct. Okay, in a way that is correct, it will get bigger. But which parameter is getting bigger or larger or increasing or decreasing? You can see that I even put the value here. Okay, so pressure or temperature, we can answer pressure or temperature, but we focus on the pressure for turbine. Okay, please remember that. I have explained.
Noted.
So pressure. Okay, back to your sketch. So it will get bigger. Okay, if this is your TS diagram, T means temperature, S means entropy. Okay, I think when you try to sketch like this, increasing like this, I think you maybe in your head you're thinking about volume increasing, but we are in TS diagram, so the volume, the line of the volume is not like this. Okay, so okay, the volume increase, but the temperature and pressure decrease because you expand, you decrease the pressure. So when you decrease the pressure, you decrease also temperature. Okay, so decreasing. Something like this. Okay, so this is at the inlet point, number 1. This is outlet exiting the turbine. Okay, this is ideal cycle. For actual cycle, we assume it is a straight line. Why straight line? For ideal, this is ideal. The dot line is ideal. This one is apa tu? Actual. Okay. Okay. So like this, the process. This is actual. This is ideal. Or we call it isentropic. So that's why the entropy for ideal cycle, the entropy is the same. Okay, we assume that there are no energy loss, so entropy constant. So that's why it is a vertical line. Same entropy for 0.1 and mentioned 0.2 prime. Okay, this is ideal cycle, but the actual one is this. The actual one that occur in the exercise one is this one. Okay, everyone understand? Okay, later on in your final exam, I ask you again to sketch. At least you have to sketch. You know how to sketch. Not the correct value. You don't need to put the correct measurement, the correct scale, etc. But at least you sketch. You know how it's increasing. How the temperature line, pressure line on the TS diagram. Okay. Okay. So temperature decrease, pressure decrease. Okay, so now we can calculate. So I've mentioned just now by using the value at the input and output, pressure and temperature. In order to calculate isentropic efficiency, we need to search first with the data given. We need to find first the enthalpy, the entropy. Have you found that out? Okay. For example, for state one input. State 1 input, 3 megapascal, 4 degrees Celsius. So what is the enthalpy? Anyone can give me which table you're looking at? I asked.
I have a question for the expansion. If in the expanding sense, shouldn't is the pressure with the isentropic efficiency, is it proportional, or it does not have any relation with the pressure?
For isentropic, this one. The pressure.
Mhm.
This is actually the isobar line. This is okay. So at state 1 3 megapascal. So state 2 50 kilopascal. Okay, at the exit. Okay, it is a steam. So the process, we assume that the process occur outside the mountain of the TS diagram. This mountain, right? You have this mountain, right? Remember? Okay, in a TS diagram. So because inside here, only liquid plus vapor. Okay? Here is vapor and here is totally liquid. Okay? So this is the isobar line. So at the isobar line inside the mountain or the phase change here, it is horizontal, just like temperature. Okay, horizontal line. But outside the mountain here, you have the isobar line, something like this. Okay, it has like a slope. Okay, so even for ideal case, isentropic, the pressure still will change from 3 megapascal, the pressure the same, 3 megapascal to 50 kilopascal. Okay? Just that temperature is different. Temperature at 0.2 is different than the temperature for the ideal case 2 prime. The one that we need to find out. Okay, but the pressure is the same. Okay, so, okay, Marwan?
Yes, Doctor, thank you so much.
Okay. Oh, sorry, I didn't project the slide, but I think you can look at the whiteboard. So what is the enthalpy and entropy for first point first? I want to ask Kartikan. Kartikan? Kartikan, are you there? Kartikan, if you're not there, so I consider you are absent today, okay? Okay, I ask somebody else. Khairul Rushdi.
Yes, Doctor.
Okay, can you give me for input, only input first. Okay, at the input we have 3 megapascal, 400 degrees Celsius. What is the enthalpy and the entropy at that point? By using table, you don't need to calculate. You use table, but which table which table we can use?
Table A6, Doctor.
A6. So, okay, what is the value? Give me the value of the enthalpy and entropy from the table.
The enthalpy is 3231.7.
Okay.
The entropy is 6.9235.
Okay. What is the name of the table? Yeah, table A6, but what is the name?
Superheated water.
Okay, superheated water. Okay. Okay, thank you, Kairosh. Guys, I want to explain why we use superheated water, or why we assume that it is superheated. Okay, so that's why it is important to sketch first. When even though the question didn't ask you to sketch or anything, for me, my method is to sketch first. Okay, to approximate first, or the location of the input output etc. in a TS diagram. Okay, so if why we use superheated water? Okay, in the TS diagram here, okay, actually if you draw it properly, you have like a mountain, TS diagram mountain. So inside the mountain, we consider that the fluid is in phase change characteristic, so liquid plus vapor. Okay, beside here, this is totally on the left hand of the mountain is the liquid, totally liquid, only liquid, and on the right is totally vapor. Okay, totally vapor. So the process in the turbine usually usually the process in the turbine occur where when the fluid is in vapor state, only vapor, this part. So that's why I draw just now this part, and the mountain is on this side. So it is outside the liquid vapor. So this is vapor, totally vapor. Even if you go higher than this, it will be superheated vapor or dry vapor. Okay. So this part is totally vapor. Okay. So because when it enters the turbine, exiting the combustion chamber or boiler evaporator, etc., it was at higher temperature and pressure. So it is very difficult to consider that the at the inlet is wrong. Not is wrong. It is quite impossible. Okay, to consider that the fluid at the inlet of the turbine is still in the liquid vapor phase. Okay, because the function before the turbine we have evaporator or boiler, right? So the evaporator the function is to evaporate. So normally we will try to evaporate until it become totally vapor. So means that the state of the fluid at the turbine inlet is vapor, or at saturated point here, saturated vapor. This is saturated line, so saturated vapor. Okay. So that's why we use the table superheated water. We consider that it is at vapor state, vapor phase. Okay, totally vapor phase. So okay, thank you, Carol. Okay, next one. So you have that value, keep that value first. We will use that H1S1 for the calculation later on to get the isentropic efficiency. And then for at the exit of the turbine, we need to find these two value, 2A and 2S. Okay. Okay, because the point for 2A and 2S are different. Okay, thank you, Tension. If you want to write the H1S1 on the whiteboard, you can. 2A and 2S, find 2A and find the enthalpy at point 2A and the enthalpy at point 2S also. Because we know the pressure is 50 kilopascal, 2A and 2S are the same. And the temperature for 2A is 100 degrees Celsius. Right, because given the turbine, the steam leaves at 50 kilopascal and 100 degrees Celsius. So this point is 100 degrees Celsius. Okay, for 2S we don't know. Okay, it's not given. But temperature for 2A is 100 degrees Celsius. Okay. So we can find the same method as just now for number 1. We can, because we know the temperature, we know the pressure, so we can find the enthalpy H2A for this one. For 2A. Okay. Later on, we will find the point 2S. 2A first. So what is the enthalpy? H2A. What is H2A? Okay, someone, okay, I have to call out. Apa outlet ni? 2687 H2A, you mean Marwan? H2A. H2A, okay, the actual outlet 2687, okay. Okay, I can accept the answer. Okay. And then we need to find the for point 2S. Okay. For point 2S, the isotropic point. Okay. For point 2S, what do we know about point 2S? We know that the pressure is the same, 50 kilopascal. Other parameter that we know for 2S, we don't know temperature. We don't have the value of the temperature of 2S, but what else do we have? What do we know about 2S? Another parameter. Someone can answer me? Apa yang 2682 tu? Oh, okay, tadi ya. Okay, 2687, 2682, both are okay. Both are fine. Both are correct. Maybe Umi, for point 2S, other than, we know that 2S, the pressure is 50 kilopascal. What else, what other parameter that we know about the location 2S?
We can get the temperature.
Temperature, how? Macam mana? Directly from here, we don't know the temperature. Temperature 100 degree tu daripada 2A.
Table.
Sorry, table. Table mana? Table mana, sorry? Actually, you have one other parameter that you don't have to calculate, but we can use it from the previous point. Tak payah calculate lagi. Ada satu lagi parameter yang tak payah calculate. Awak boleh dapat apa parameter tu untuk 2S. Tengok dekat diagram ni. 2S tu kan, dia, macam nak cakap, apa yang constant? Apa yang constant?
Entropy.
Entropy, okay. So that's why we assume it's entropy. So that it's easier for us to guess the entropy. So the entropy of at the location 2S is what? Apa entropi dekat 2S tu? Sebab dia constant kan, so dia apa? The entropy is the same as what? Same as S1, okay? Umi faham tak?
Oh, I see. Okay.
Kan, so the vertical line.
By the way, for H1, bukan ke
apa, you dapat value lain sikit, lari sikit kan?
no, it for pressure 3 MPa.
3 MPa, betul?
And then the H1 is 3231.7. The one at this
Oh, tension tadi just now.
it's for 2.5 MPa.
Okay, maybe okay. I don't remember who answered the one just now. Marwan, I think. But when Marwan answer, I think Marwan mentioned 3237 or something like that. Okay. Khairul. Sorry, Khairul. Khairul. Okay, 3237 kot. Kau 311 tadi dah betul dah. Correct. Just that bila tension tulis ni yang lari sikit. Because okay, sometimes the table have different version, edition. Edition, 7th edition, 8th edition, and sometimes the value they put in the table apa tu quite just slightly different. Okay, because the book has several edition if we have evaluated, so sometimes the table, the value in the table tu dia memang ada sikit berbeza. So kadang tu saya terima je, I accept because the edition of the book, the table tu. Okay. Okay. Betul tadi. So S2S is the same as S1. Okay, everyone understand why it is the same as S1? Because we assume ideal case. So ideal case means that no energy loss. So no energy loss means that entropy is the same. Not that entropy is zero. Entropy is the same. Okay, maintain the same. Okay, so maintain the same from the inlet to the outlet. From point 1 to 2S. Okay, so at point 2S, okay, actually the state, the phase of point 2S, actually what I draw here is slightly different scale. Okay, when since it didn't mention here in the questions whether the state of at the exit of the turbine, whether the fluid is vapor or liquid vapor, right? So normally we assume that the phase, okay, of the working fluid, the steam, is still has some sort of liquid in there. Okay, means sini. So actually this one, okay, if you draw it properly, this part, sini sikit. Sorry. Wait. Saya buat balik. Mana buat balik? Okay. Thank you, tension. Okay, so if we assume point 2S, so the point 2S will be at some point inside the mountain. Means that it is at liquid vapor state. Liquid plus vapor, not totally vapor. Okay, so we want to find the quality, the X, the quality of the vapor. If X equals to 1 or 100%, means that the fluid is totally vapor. Okay, if X equals to 0, means that the fluid is totally liquid. Okay, here, at point here, totally liquid. This one, X0, the quality of the vapor. Okay, this one, at this point, X is 1. Okay, or you want to use in percentage also can, 0 and 100%. So we need to find the X, the quality at this point. Okay, at this point 2S, because 2S may be not totally vapor yet. Okay, it has some drops of liquid in there. Okay, so we need to find the X for 2S. Okay, so how do we find that? Okay, here we can use the values of entropy of point 2S here. Okay, since we know the entropy S1 and S1 is equals to S, so we use the value of the entropy to get the quality. Okay, so this is a bit of mathematics. Okay, so so this is S to S. This will be S to S. This point will be S to S. This point will be SF, and this will be SG, entropy, where the quality is the fluid is totally vapor, and this is the entropy where the fluid is totally liquid. Straight line, this is a horizontal straight line sebenarnya. Okay. So again, using table, but this time around not the same table, other table, okay, that you have already seen before this. We need to find the S2S, SF and SFG. Okay, the mixture of the fluid, the working fluid lah, the vapor, SFG. Okay. Saya kat atas. S to S minus SF over SFG. Okay. So SFG is the whole of this. The whole of from the quality at 0 until quality at 1. Okay, that the horizontal line, okay, the straight line from x0 to x1 at this temperature lah, okay, at this line. Okay, that is SFG. Okay, so we know the value of S to S. Okay, so we can search from the table SF, because we what is the name of this method? Bisection method. I'm not sure. There is a method. So you when you want to find the point in the middle, okay, it's like you calculate the whole and only consider a portion, and then you get the percentage of that portion lah. Okay, because you want to find the percentage or the quality from this one. Okay, so X to S is equals to S to S minus SF over divide by the whole line. Okay, so we to find SF and SFG from table, but which table we can use? We know pressure. We don't know the temperature yet. We know the pressure 50 kilopascal and the entropy at this one. So obviously we cannot use the same table A6 superheated, because the fluid is no longer vapor, because it is inside within the liquid vapors phase change. So which table are we using that we can use? Okay, I'm going to ask. Okay. I'll give you 1 minute to think. Okay, but mathematically you understand, right? This calculation, this like mathematic. Okay. What we calculating? Okay, from the figure, from the diagram. Oops. Okay. Okay, maybe Zainul. Zainul, are you there? Okay, awak tahu ke macam mana nak cari SF dengan SFG ni untuk point 2S? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Ya, Zainul tahu ke? Do you know how to do that? Which table?
Is it by using table A12?
Dengar sangat lah.
Is it by using the table of A12?
A12? A12 ke you mention?
Yes, Doctor.
A12 apa ya? Saya pun tak tengok. A12 apa? But obviously it's not A12, but A12 what? A12 state. Okay. A12 is refrigerant 134A. Okay. Saturated refrigerant 134A. Okay. The saturated part is correct. Okay. But our working fluid here is steam, which is water. Okay. That one in table A12, the working fluid is refrigerant. Another type of fluid, or mainly organic fluid. Okay, you understand? Faham ke Zainul kenapa tak boleh guna table A12?
Faham, Doctor.
Table A12 tu dia untuk fluid yang lain. Okay, refrigerant, which is usually we use that for a refrigerator. Dia organic fluid. Okay, so we don't use table A12, but the saturated part is correct. So we use which table? Yang untuk water. Which table, Zainul?
I'm not sure, Doctor.
Okay, saturated water. Saturated water is table A5. Okay, table A5. Just now we use table A6. Yang tadi tu, 0.1, 0.2A. Okay, 0.1, 0.2A we use superheated water, table A6. Okay, for this one, okay, since the phase at 0.2S is a mixture of liquid and vapor, so we use the table A5, which is saturated water. Okay, because in that table we have this the values for each parameter: enthalpy, internal energy, entropy for fluid, and for liquid and gas. Okay, because we don't know yet the state of the quality of the fluid at 0.2S. Kita tak tahu dia totally vapor ke, dia liquid saja ke dia campuran mixture ke, kita tak tahu lagi, kita nak kira. Okay, so we use that table because that table they give if the value of for liquid, vapor and tengah-tengah lah, kan, the middle. Okay. Okay, so we use that value. So okay, tension already write the answer here. Okay, but just want to tell everyone, each student, which table you can look at. Okay, so we use table A5 saturated water. Okay, so from the S1 that we get, S1 6.92, so equals to 2S. So we can search that point 6.92. Okay, 6.92 and 50 kilopascal. 50 kilopascal lah. Kita tahu S2S is 50 kilopascal. So around that value. Okay, around that value, so you get 6.92. S2S is, you find that value, and then the same horizontal line. Okay, you get the SF and SFG. Okay, the same line you have to find the line of the S to S first, and then you get in the same line beside it, you get the apa tu, SF and SFG. Okay, so here after calculating the quality, you get quality around 0.89. Okay, so means correct. The location of the point 2S is nearly 100%. So here lah, if you get 0.4, maybe you have to draw the location 2S here. Okay, if this is 0.4. Or maybe 0.5 in the middle. Okay? So since we get the answer 0.89, so it must be nearly near the saturated vapor line. Okay? Okay, we have really answer number 1A. Now that we have the value of X to S, okay, so we can from the same line, we can get enthalpy also, HF, HFG, okay, using the same line, the same table, HF, HFG. So from there, you have S to S. So from there, you can get H to S. Okay, say to this. Okay, so the same line as just now, when you find the SF and SFG, get also from the same line this enthalpy as HF and HFG, because we want to use it to get H2S. We want to turn around this calculation. This one is how you get the S2S. So from here, you can also H2S. So rearrange the equation, HF, okay. So this equation can be used for other parameters also, because it's just mathematical equation. Okay, so H2S equals to HF di sana, HF plus X2S HFG. Okay, the same equation as this one, except that here we use enthalpy. So rearrange the equation, because we already know X this time around. So we want to get this one, the H2S, to use it to calculate the isentropic efficiency. Okay, so this one from the same table, the same line of the table where you get S2S and SFG, the same line, the same horizontal line, you get the HF and HFG. Okay, and then include it in the equation here, and you get H2S. Okay, thank you, Tension. You get the H2S, and then so H2S berapa? And then finally, we calculate the turbine efficiency. Okay, mana lagi nak masuk? Apa? Duduk sini. Super. Hai, padam this one. Okay. Okay. Turbine efficiency, we write it like this. Okay, 2405. Thank you, Omar. Thank you, Tension also. So turbine efficiency. Okay. What if you don't remember the equation of turbine efficiency, or you cannot find it in your slides, etc. Okay, we think about like this. Efficiency, the value cannot be higher than 1. Okay, the value cannot be higher than 1. So obviously, the value that you have to put above must be lower than the one below. Okay, to get efficiency lower than 1. This one, the above value must be lower than the denominator, below. Okay, so by looking at the diagram that we sketched just now, 1 to A and 1 to S, okay, it's actually the same as enthalpy. Okay, uh, the line for enthalpy is the same as temperature. So between these 1 to A and 1 to S, which one has higher difference? Okay, this one, right? 1 to S ni. Okay, so you put H1 or temperature also can, but this we use H because we have the value of enthalpy. So we can also use the value of temperature. Okay, so H1 minus H2S, because this one, okay, if you look at here, the difference is higher compared to just to A, this is lower. This is A, this is S. This is higher. This is the difference smaller. This is bigger. So the bigger one we have to put below. And the higher one, at the above is H2A. Okay? So that the efficiency obviously won't be higher than 1. But for compressor is the opposite. So that's why you are encouraged to draw the sketch the process in the TS or HS diagram of for compressor, and then you can get the equation for turbine efficiency for compressor efficiency as well. And we start with H1, the input, because the value temperature and pressure for one is higher than at the exit. Okay, we want a positive value. Okay, so this is the turbine efficiency lah. Okay, and B, you calculate this one because you already have H2A. Mana H2A? This one H2A you have, H1 you have, H2S you have. So just calculate. Okay. Okay, next, the mass flow rate of the steam. So normally for thermodynamic or propulsion later on next semester, the first part of the question usually is harder or longer than the second part. Because in thermodynamic or propulsion, we need to define first the process, the step by step, which one goes first, and then the cycle, right? To understand first the situation, that's why we need to sketch in a TS diagram, etc. So once we already located all the points, we have all the input parameters, we already defined the input parameters. Usually the second question or third question or after that is easier, usually is more direct calculation. So the harder part is the first to really understand the situation of the process, the thermodynamic process. Okay, so the second part, the mass flow rate of the steam flowing through the turbine. So the mass flow rate entering and exiting the turbine. Okay, so we assume the mass flow rate is constant, doesn't change, inlet outlet. So what is the mass flow rate? So knowing we will use enthalpy here, okay, and knowing the energy balance for turbine. Remember first law. Okay, this time around we use first law because we need that energy balance, first law. So in a turbine, which energy we have in the turbine, which energy or which work or heat transfer. Do we have heat transfer in the turbine? Miza, ada heat transfer tak dalam turbine? Turbine ni, exercise 1.
Tak ada.
Tak ada Why?
Sebab dia adiabatic.
Okay, Alhamdulillah awak jawab tu. Okay, adiabatic. Okay, actually sometimes if it's not adiabatic turbine, sometimes there is some sort of change of heat. Okay, maybe there is heat transfer, heat exchange, Q. Okay, heat exchange within the turbine, but usually is smaller than other component, work or enthalpy, etc. Okay, so sometimes that's why we neglect. But here it's clearly stated that the turbine is adiabatic. Okay, so adiabatic, so we can assume that the no heat exchange, no Q, the Q is negligible. Okay, next, do we have work? Okay, do we have work output or work input for turbine? Syed Hamdan, Abdullah Syed Hamdan, do you have work output or work input in a turbine?
Yes.
Yes, work output or work input? Sorry, I cannot. Input or output? Work.
Input.
Input?
Oh, no. Sorry. From the turbine work output.
Yes. Okay, you shocked me. Okay, work output or power output. Okay, work is in joule. So if you change into watt, it's a joule per second, so you get watt power output. Okay, so turbine produce power. It produce power to for electrical power and to be used back in the compressor for electrical use in the compressor. And what else? We have the energy transfer by mass, which is enthalpy. Okay. So using the energy balance of the first law, we change to the third whiteboard, third slides of the whiteboard. The energy balance for turbine, okay, input equals to output. So at the input, okay, here we have at the input we have the mass flow, the energy transfer by mass at the input 1. Okay, no work input, no heat transfer, so only heat energy transfer by mass H, which is enthalpy. And then at the output we have the energy transfer by mass again, enthalpy, plus the work output. Okay, no heat, no kinetic energy, no potential energy. Okay, so from this one, we know work output. We want to get the M. So senang lah kan. So we want to get the mass flow. So you H2 minus H1 kan, plus H2 minus H1 minus H, because H1 is higher than this one. Kita buat oops. H2A. We do one by one lah. Okay. Okay. Susah. Okay. Pening. Tengok sini dulu. H1 minus H2. Okay, equals to W out. Okay, and then M. W out. H1 minus H2. Okay, H2A lah, actual lah. Now we use actual value lah. Actual value of the process. Okay, so M, that is M dot lah. So W out is 2 megawatt, and H1, H2A you already get it previously from the previous calculation A. So you get the mass flow rate lah. Okay. So that's it. So how much mass flow rate? Uh, 2 megawatt divide by enthalpy H1, H2A just now. Okay. Okay, you guys can do it individually, kesian Tasha seorang. Okay, okay, so we can look at the exercise 2 again, steam at 7 megapascal and 450 degrees Celsius is throttle in a valve. Okay, so this one we use a throttle valve to a pressure of 3 megapascal during a steady flow process. So this one is kind of like expansion process juga, it's the same because we decrease the pressure 7 megapascal to 3 megapascal during a steady flow process. Determine the entropy generated during this process and check if the increase of entropy principle is satisfied. Okay, it's okay. We search the entropy generated first. Means that S2 minus S1. I mean at the exit minus S entropy at the inlet. You want to see the change of the entropy generated, right? Okay, so so kind of like the first one exercise. So we have pressure and temperature. So try to find enthalpy if you can, enthalpy, entropy from a table. Kau apa dah? 11, 12. Okay, while doing the exercise 2, we can if you want you can take a break, maybe just 10 minutes, okay? If you don't want to take a break, you can think you can do the exercise 2 until 11:22 je. Okay? Okay, if some of you are here, I think I want to skip exercise 2 because we're already 11:20. But just telling you, exercise 2 is quite the same as exercise 1. It's just that for throttle valve, we don't have any for energy balance for throttle valve. We don't have no heat transfer, no heat exchange, no work output. A valve is like a pipe, pipe to drop to decrease the pressure. Okay, the function. So you don't have any heat transfer occur. You don't have any change, any work done, work output or work input, and there's no also potential energy or kinetic energy. So you only have energy transfer by mass, which is the enthalpy. Okay, so here you can assume that H1 is equal to H0, H2, H0, H2. Okay, I just write down on the whiteboard here because I want to go quickly to exercise 3. Exercise 3 is more important concerning the ideal jet propulsion. I'm afraid that we don't have enough time for me to explain the example of ideal jet propulsion before your final exam. Okay, okay, so the throttling valve, the same table, the same method as exercise 1, just that the energy balance. So this one 0, no output work. Okay, so you only have the H out output minus H inlet. So no potential energy, no kinetic energy. Okay, this is from theory of for throttling valve in your chapter 5, 6 like that. Okay, so this one 0, this one 0. So you only have this. So by using this, we know that H out is equals to H in. Okay, so you can use this assumption. Okay, so you will get H2 equals to H1. Okay, it's because later on if you look at the table, the same method as exercise 1, you have pressure, you have temperature, so you look at the table A6, you get entropy and enthalpy. So you can assume that enthalpy doesn't change. So enthalpy input and output is the same, 2 and 1 the same. So by using the same value of enthalpy, we search back the entropy, okay, S2. So from here you get back S2, okay. And then to calculate the entropy generation, S2 minus S1, use pointers. Okay, and this is entropy generation equals to 0 because it is steady flow. Steady flow, so here actually ds over dt. The rate of change of entropy, but steady flow, so this value will be 0. So this one you get from here, okay, S2 and S1 using the table. So you get the entropy generated. Okay, okay, I want to pass exercise 2. Okay, we do exercise 3, okay? Because it concern aircraft engine lah. Okay, and we haven't done this example of exercise yet. Okay, start with this one. Okay, for ideal jet propulsion cycle, ideal. So a turbojet aircraft flies with a velocity of 260 meter per second at altitude where the air is at 35 kilopascal and 233 Kelvin. The compressor has a pressure ratio of 10 and the temperature of the gas at the turbine inlet is 1373 Kelvin. Air enters the compressor at a rate of 45 kg per second. So determine the temperature and pressure of the gas, the velocity and the propulsive efficiency of the cycle. Okay, so turbojet is one type of a jet engine cycle. So we use the Brighton cycle, the Brighton cycle gas turbine cycle, right? Okay, so Brighton cycle the same as the power plant just now. Just that for turbojet it is open cycle. So we have to determine the temperature and pressure of the gas at the turbine exit. Okay, so we must locate first the point of each of the process. Okay. So the same as just now, we try to draw it in a TS diagram. Try to locate first all the point of the process. So, so we start with from 1 to 2. We start with what? I've slightly mentioned it just now. Example for aircraft engine, the first component previously on the exercise 1, I did explain a bit about aircraft engine cycle, jet engine cycle. So the first component is what for jet engine cycle? Amirul Akmal, are you there already? Amirul Akmal di situ tak? Otherwise, I will call you back after this. Okay, tak apa, panggil orang lain dulu. Siapa lagi? Afiq.
Ya, doktor.
Okay, first component dalam turbojet engine or jet engine apa? Macam tadi kalau power plant kita start dengan compressor atau pump kan? Kalau yang ni dia first dengan apa?
Turbojet engine, start with motor.
Start with?
Motor, no.
Motor?
Yeah.
Oh bukan. Ini dia macam dia macam thermodynamic cycle gas sebab dia guna the same cycle juga as gas turbine power plant cycle dia, cuma dia ada two extra component. Actually tadi I already mention in exercise 1, slightly saya dah explain kalau you rajin nak pergi tengok balik page 1 punya whiteboard. So the first component tu apa? Kita start dengan apa aircraft engine? By now you already in not just for aerothermodynamics, because you are in aerospace engineering program. So and second year already, so I think you must know the things the component, the main component in an aircraft engine, kan kena tahulah kan nak jadi aerospace engineer, at least aircraft engine tu ada apa. Engine kita cakap dengan engine saja, tak cakap dengan apa dia punya sayap, dia punya apa tu, tak cockpit ke apa ke tak. Tension measure compressor. No, bukan. For power plant, yes, we start with compressor. Okay, gas turbine power plant, yes, we start with compressor, but for aircraft engine, no. There's another component before that. Inlet intake, okay, inlet intake is the process, but what is the component to use to like intake fan. Okay, maybe okay, fan for turbofan, yes, you have a fan, fan which acting like a compressor also, fan. But there's another component. Okay, diffuser. Okay, tension. Afiq jawab turbine. Salah. Turbine belakang-belakang tu Afiq. Yang macam tadi. Dia lambat lagi. Dia lepas combustion chamber. Okay. So diffuser. Okay, diffuser. Please remember. So diffuser, the function is opposite than the nozzle. Nozzle at the exit. Nozzle kan kat exit kan. Nozzle, we want to increase the velocity of the gas to high speed gas flow so that we can produce thrust. So diffuser terbalik. Opposite. Diffuser at the beginning. Okay, we have a diffuser to decelerate. If for nozzle to accelerate, diffuser to decelerate, to slow down. Okay, because we want to like capture the air intake so that the air can be enter in our compressor in the core engine. Okay, so we start with diffuser. So 1 to 2 is the diffuser. So this is diffuser. Saya tulislah kat sini. Diffuser. And then, so diffuser in a TS diagram is a straight line like this. This is an ideal case. Okay, so diffuser, we for ideal case, we assume that no energy loss. So entropy is constant. Okay, not that it is zero, it is constant, 1 to 2. And the pressure, the temperature increase a bit, just slightly, just small line, okay, not too big, okay, the line 1 to 2, just a small change in temperature. And then what else? Okay, after diffuser. What is after diffuser? Just now you mentioned?
Compressor.
Yes, compressor. Okay, after diffuser, you have compressor. So ideal. So straight line, compress, increase pressure and temperature. Next, after compression, Amirul Akmal aja orang lain. Wait, others, because just now I was asking Amirul Akmal. Are you already here? Amirul. Wait, wait. Ada student wait. Amirul? Ada tak kat situ? Ke ada mic problem? If you have a mic problem, you can check in the chat box. Okay, Syed Hamdan, benar slide the function is kind of like the same as benar, but for jet engine usually what we use what? We use the term what? Apa nama? What is the component? Benar, yeah. Okay, we can also call benar, but there's another name. Combustion chamber. Okay, combustion chamber. I prefer use this one. Okay, combustion chamber. Okay, so combustion chamber increase temperature and pressure. Of course, you mix the fuel, your fuel, diesel and kerosene with air, oxygen. So combustion process will occur. So you increase temperature. Okay, but for ideal case, we will assume no pressure loss during the combustion process. So this is constant isobar line, constant pressure. Increase temperature but constant pressure. Okay. Ideal case, okay. Of course, in actual case, there is some sort of pressure loss. Okay, so the pressure at 0.3 and 0.4 is not the same. Okay, next, after combustion chamber, so this is CC, combustion chamber, this is compressor. So you have to know all the components in the basic jet engine. You are in aerospace engineer program. So after combustion chamber, which component? Wants to give the answer? Turbine, okay, turbine. So just like the power plant just now, so you have turbine. So turbine like this, straight line, straight vertical line, should be straight vertical line. So turbine, you decrease pressure, you decrease temperature. And finally, after turbine, what? Nozzle, okay. Thank you everyone. Nozzle, okay, just look at this part. Compressor, turbine. Diffuser, nozzle. So that we can complete the cycle. Otherwise, we cannot complete the cycle. Okay, so nozzle. Nozzle to increase the kinetic energy, okay, to increase the velocity to high speed gas flow. So normally we will do like this, dot line. because it is open cycle. Okay. Okay, so this is the basic component in aircraft engine. Just now, the temperature and pressure of the gas at the turbine exit. So turbine exit is point number 5. Okay, this one. So we want to find, the first question, we want to find pressure and temperature at the exit of the turbine. So P5T5. Okay, P5T5. Okay, but normally for thermodynamic or propulsion, even though the question asks you to calculate P5 at the turbine exit, which is location 5, we need to start from the first point, from when the working fluid entering the engine or the cycle. Start with point 1, point 2, point 3, point 4, and then we can get point 5. So we have to start from the beginning. We have, at least we check do we have all the parameters? If you already have the parameters at point, which is pressure and temperature, usually we need pressure and temperature. Do we have pressure and temperature easily from the question? P1 T1, if you already have, don't need to calculate, so you proceed with P2 T2. So you just look back. Okay, but for here, this one, P1 T1. Okay, look at the questions. Okay, look at the question. So in the diffuser, okay, diffuser. So we want to get P1 T1. What do we know? We know the parameter at point 1. Okay, the parameter at point 1, P1 T1, where the air is at 35 kilopascal and 233 kilo. Okay, let's first arrange all the values that we have first. For example, okay, we know P1 35 kilopascal. Okay, so this is how I prefer or I advise you guys to do when you have this problem in your final exam or what. Okay, try to, other than sketch the diagram, try to locate back, okay, all the information that you have, all the data that you have from the questions, try to write back. Okay, so P1 35 kilopascal and 233 Kelvin. Okay, the ambient at point 1. Okay, and what else? Compressor has a pressure ratio of 10. So pressure ratio, okay, if you look at the compressor is 0.2 to 3. So pressure ratio will be P3 over P2. The ratio. Okay, P3 over P2. So P3 will be 10. The ratio is 10. Okay. What else? And the temperature of the gas at the turbine inlet. Okay, this is also normally a parameter given because each turbine, each engine has different characteristic of turbine inlet temperature. Means the highest temperature, the maximum temperature that the engine can withstand, boleh bertahan lah. Kan? Because 0.4 is the highest point, right? The highest point of the cycle is 0.4. So turbine, we need to take into consideration what the value of T4 because this is at the highest temperature. So depends on the material of the turbine blades. So each turbine maybe has different maximum temperature that it can withstand. So this is usually a characteristic of a turbine and the engine. So turbine, so T4, 1373 Kelvin. Air enters the compressor at a rate of 45 kg per second. So this one we also know the mass flow rate here, 45 kg per second. Okay, usually the mass flow rate doesn't change except during this because here we will include fuel. Okay. At first only air. air intake, right? 1 to 2 to 3, 2 to 3 only air. And then we add fuel. So the mass flow rate of the fluid in the core engine, this is all the core engine, after entering the turbine will be M air plus M fuel. Okay, because we inject fuel here in the combustion chamber. Here only MA, air. Okay. Okay, now we can start the questions. The temperature and pressure of the gas at the turbine inlet. Temperature and pressure of the turbine at the gas temperature of the gas at the turbine inlet. Outlet. So T5, P5. Okay, so we have P1, T1. So next our task is to calculate P2, T2. Pressure and temperature at point 2. What do we know about diffuser? Because point 2 is exit diffuser. What do we know about diffuser? What is the function of the diffuser? So we use that understanding that knowledge to calculate P2, T2. Saya kena cepat we have to because you're already 11:45 41. Okay, I turn to the next page. Okay, remember diffuser. Okay, energy balance for diffuser. Diffuser, no heat transfer, heat exchange. Okay, again energy balance. No heat exchange, no work output, no work input. Diffuser, you don't need work and you don't produce work. All of these are in the previous chapter slides, lecture. Okay. And then enthalpy, of course. There is enthalpy. There is kinetic energy because we are slowing down, we are decelerating the air. So there is the change in kinetic energy, but there is no potential energy or very, very small potential energy. So we neglect that. So we only have enthalpy and kinetic energy. Okay, enthalpy and kinetic energy. So input, output. So at the input, the energy at the input, kinetic energy, equals to energy at the output. Energy balance, this is from the energy balance, nothing new. This is energy balance, except that usually we always consider the kinetic energy zero, negligible. But now, since it is a diffuser, from 1 to 2 is a diffuser, so diffuser we cannot neglect kinetic energy. There is change in kinetic energy. Okay? Diffuser and nozzle, we cannot neglect kinetic energy because that is the purpose after all. Okay, the purpose is to decelerate and accelerate, so there must be change in kinetic energy. Okay, so in ideal case, diffuser, what is ask yourself again, what is the function of diffuser? We want to decelerate, okay, to slow down the air, okay, to a complete stop if you can, actual case, to a complete stop before entering the compressor. That is the function of diffuser. So if we said to decelerate the air in the diffuser to a complete stop, means that V2 at the exit of the turbine, 0. Okay? Because the function of diffuser is to decelerate the air intake to a complete stop. Ideal case, to complete stop. So V2, 0. So you only have H1, V1, H2. Okay, and then from here, H2, H2 minus H1 minus V1 square over 2 equals to 0. Okay, enthalpy, remember, enthalpy we can also write, if you don't know the value of enthalpy, we can use this one. In the case, because we want to get the temperature, so that's why we use this one. Okay, enthalpy DH, the difference equal to Cp dt. This is from the entropy chapter. Okay, you have this one. So you use to translate this to this. Okay, we assume specific heat constant, which is for air, the specific heat will be 1.005. This will be given kalau if it's given here Cp 1.005. Okay, I don't need to write it here. Okay, so equals to 0 here. So V1 in the question, V1, a turbojet aircraft flies with the velocity of 260 meter per second. So that is your V1. Okay, the initial velocity. V1 260 and T1 2T3 just now, Cp 1.005 kilojoule per kilogram per Kelvin. So you get T2. Okay, so you find T2. You have all the value here. T38. Tak tahu. You dah calculate Okay. Okay, so don't forget power of 2 square. So you get the T2. Okay, wait. For this, since this is you need to use SI units, so yang DCP keep it in joule. Okay, so 1005. Otherwise, you won't get the correct value of temperature. Okay, use 1005. So you change in joule. SI units. So so T2, and then how are we going to get pressure? So for entropy, isentropy, ideal gas case, ideal gas case, we have this relation of pressure and temperature. Remember in chapter 807, 809, the TDS relation, the chapter TDS relation. So we have this K or gamma. I usually use gamma. Okay, this relation is valid for isentropic ideal gas. Okay, so you can use this relation. So you have T2, you have T1, we have P1. So gamma is a constant, 1.4 or 1.33, depends. What do we use? We use 1.4. Okay, 1.4. So you get P2. Okay, so you can get P2 from this relation. Okay, get P2. Okay, any questions so far for diffuser? Okay. This method you have to we use a lot in propulsion next semester. So we introduce first in aerothermo, and you continue for actual case, second two stage, two spool, turbofan, all in propulsion. Okay, so you get T2, P2. I'm rushing, so that's why I didn't develop into detail, but I guide you. Okay, I guide you. So you use this isentropic ideal gas relation, you get P2. Okay, next, and then for point compressor, remember the compressor just now, we have pressure ratio. So we use that pressure ratio value. So this one quite direct. Okay, you get P3, because P3 over P2 is the pressure ratio. So once we have achieved P2, so we can get P3. Okay, from here, from the pressure ratio. Okay, this one easy. And then the same relation of T3, T2, you can get the simulation of pressure and temperature, you can get this time gamma minus 1 over gamma. So from here you can get T3. Okay? Since you have P3, you have P2, you have T2, so you can get T3. Okay, from the same relation as previously, because compressor also are still ideal gas, isentropic, etc. So isentropic straight vertical line just now, our diagram, our schematic diagram. So we can use this relation. Okay, and then for the combustion chamber part, okay, combustion chamber slightly different. Combustion chamber slightly different. Okay, okay, the change in energy for combustion chamber, if this turbojet that we are considering is ideal case, so we consider that all power produced by the turbine output all will be used in the compressor with no any energy loss. Okay, ideal case, all the power produced by the turbine will be used in compressor. Okay, ideal case. So from here, work, okay, energy balance. So the work for turbine, energy balance, first law, is equal to the enthalpy, because turbine, other than power output, you don't have heat transfer, you don't have kinetic energy, you don't have potential energy, so only work and enthalpy. So the same as compressor, only work and enthalpy. So W compressor work will be equal to H3 minus H2. Okay, so H4, this one, the same as just now. So you use CP T4 minus T5. Okay, CP delta H just now. So this one also CP T3 minus T2, like this. Okay, so we cut this out. Okay, so from here you can find T5, because you know T3, you know T2, and you know T4, 1373. So you can get T5. Okay, T5 here. Temperature exiting the turbine. And then the same relation, this one, same relation. So you put same relation. Okay, next page. So you put P4 over P5 just now equals to T4 over T5, the same relation as the compressor. You have gamma minus 1. So you have T5, you have T4, you have P4. Okay, P4, because P4 is equal to P3. Just now, look at this one. P4 equals to P3, constant pressure, okay? So don't need to calculate P4 anymore. P4 equals to P3. Okay, we want to find P5. Okay, go back. So P4 equals to P3. So this one you have. So you need only P5. Okay, so rearrange your equation. So you get P5 from here. Okay, so finish the A. And then next, the velocity of the gas. Velocity of the gas at the nozzle exit. So nozzle exit 0.6. Okay, so nozzle opposite of the diffuser. So you use the same, this one, H6 plus V6 square over 2 H5 over 2. Okay, the same as diffuser just now. Okay, just that this time around nozzle is opposite. So nozzle, the function is to accelerate to high speed gas flow. So we assume that because just now we assume in the turbine no kinetic energy, only work output and enthalpy, right? So means that okay, so means that, okay, then this is nozzle 5 to 6. So means that at this point, exiting the turbine, no kinetic energy. Okay. So at this point, V5 is 0. No kinetic energy yet, negligible. Okay. So this one 0. Okay. And then we will accelerate the fluid until higher possible that we can get lah. Okay. So we can get V6. H6, okay, using the temperature. Okay, macam mana tulis ni? Okay, okay, V6, okay, V6 square over 2 H5 minus H6. So you H6 minus, if we turn around the, okay, so T6 minus T5. Okay, we already have T5 just now. And T6 you have to use the same, this one. T6 sama juga yang ni. Tulis P5 sebab because the nozzle, the function is the same as turbine, like the diffuser just now. So you can use this one. T6 gamma minus 1. So from here you get T6. Okay, T6, huh? So this T6 that you are going to use here. Okay, P5 already here, P5 here, T5 previously. Okay, and P6 is the ambient, back to the ambient at the beginning, 35 kilopascal. P6 equals to P1, the ambient pressure equals to P1. Okay. So you get T6. So this T6 you put here. And you get V6. Velocity at the exit. Okay. The propulsive efficiency, actually you just need to use the formula. The formula is in this slide. Propulsive efficiency. Propulsive work first. The thrust work, M dot. M is given the V at the exit, which is V6 minus the V at the inlet just now, V1. And the velocity of the aircraft is equals to this, at this point, V1, V aircraft is V6 also, V1 also. So this one is equal to V1. Okay, so you get the propulsive work, and then Q in also, Q in the combustion chamber. Okay, combustion chamber, so Cp dt is enthalpy. Use the enthalpy. H4 minus H3. So and then from there you get the propulsive efficiency. Propulsive efficiency is the WP output over Q in the combustion chamber, the input, the fuel input. Okay, this one M dot actually okay, tak apa. Cp T4 T3. Okay, so you get this one, propulsive efficiency. Okay. Just one moment. Before we leave, okay, we exit. I would like you to answer this survey. Okay, silap sekejap. This one, okay, not this one. Ada satu lagi. Wait, aerothermo. But the question is the same. Kejap this one. Okay. Sekejap. This one. Okay. I would like you to answer just a simple survey, I think. Okay, like 10 questions here, if you don't have any extra comment to give. But this is a survey on the content of this course lah, Aerothermo. Okay, so ada tu kali tanya email ni. Actually, don't need this one. Okay, refresh. Wait. Okay. Okay, so just answer the survey about the content of the course. So I'll give you the link here. You can do it just 2-3 minutes now. Please, I just would like your feedback on the content, okay? So if you can answer the survey first before you leave. Okay, I hope that all of you can answer this one. We have around. Can you open the link?
Can.
Okay, boleh Okay. So about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And plus any comment or suggestion lah. Okay, otherwise, while you are answering, I explain a bit about the final exam. So, of course, all topics will be included, but I will focus more on the second law, but not saying that first law will not included anymore. Okay, so of course, like you've seen our exercise just now, in order to apply the second law, you still need to know the energy balance, the first law, etc. Right? But the detail maybe not as the detailed calculation is maybe more on the second law. Okay, because the first law we already done assess in test 1, right? Okay, but you still need to study, at least you know, because you need to apply the energy balance, etc. Okay, so there will be 2 parts, part A and part B. The same question as Dr. Izani's group. So all your batch will answer the same questions. Okay, Umi left. Okay, your batch will answer the same final exam questions. So part A and part B. Okay, so part A, there are 6 questions on theoretical open-ended questions. No calculation. Part A, no calculation. You just need to answer, give your opinion on the questions, suggestion, predict performance, etc. But without calculation. So part A, there are 6 questions, but you need to answer only 4. Okay, I repeat. There are 6 questions. You need to answer only 4. So each question is 4 points. So saya tulis kat sini. So part A, answer. But of course, the instruction is given also on the front page of the final exam. Just telling you here. Answer only 4 questions out of 4. Out of 6, out of 6. And each questions 4 marks. So 4 times 4, 16 for part A. 4 marks. So total will be 60 marks for part A. Answer only 4 questions of 6, each questions 4 marks. Okay. So part A is theoretical, but not exactly 100% like directly from the lecture, but of course you have to think it's open, since it is open book, so we cannot ask directly like just direct question lah. Okay, so theory from lecture notes, okay, but it is open-ended. Okay, part B is calculation, like what we have done in tutorial exercise. Okay, so part B, answer only 2 questions out of 3. Okay, So each question will account for 12 marks. So 12 plus 12, 24. So total part B, 24 marks. Okay, so 24 plus 16, 40 marks. Okay, so 40% accounted for 40% of your final exam. So direct calculation we use direct calculation. Okay, so you get 16, 24, 40 marks for your final exam. So part B is like what we have done usually in exercise, tutorial, etc. So you have to answer 2 questions, but of course inside the 2 questions there is A, B, C or A, B, like that. Okay, there is small part calculation. So part B is calculation, performance calculation, the cycle, etc. Okay, so that is your for your final exam. And okay, for your carry marks, okay, I have marked all the, of course, the test. You already know your marks for your test and the assignment, quiz. You don't have quiz. You had homework, right? Assignment homework. Okay, so of course I have all those marks which is equivalent to 30%. I'm not sure if you want me to share that 30% first, because another 30% is for your last assignment project, right? Your mini project. So that one I have extended the deadline until final week of the final exam, which is 18th February. So just that the constraint is that I cannot give you the full carry mark before your final exam. Okay, because the another 30% is on the final assignment that you yet to submit. So I only have the 30% mark. You want me to share that 30% first, or just no? Otherwise, I cannot. Since you did not submit yet the assignment, the final assignment, you won't know your total carry mark lah. Nanti even after your final exam tak tahu juga. I cannot tahu lah. Okay, so I share first the that 30% lah. At least that 20% you already know from your test. So just plus 10% from the homework. Okay, so not too much lah. Okay, so I sorry, response. Okay, I have received 7 response. 7 response. This is nothing to do with your final exam or teaching assessment or what. This is actually because I've mentioned in the first week of the class that this course I do it also for the Erasmus European Union project. So we want to get some feedback from the students after finishing the course at the end of the semester. Okay, so that is the purpose lah. Okay, nothing related to your UPM or your CGPA or anything. Okay, so seven respondents. I need 5 more. 5 more response. 6. You guys are 13 total. So 8. Okay, now 5 more. Okay, you can see your ID here that you have submitted. Okay, 5 more. Apa tu? Oh, questionnaire. Okay, I prefer you answer directly right now so that you won't forget. Otherwise, you will delay to answer the survey. Okay, 9 response. 9 for 4 more. Ada semua 14. Oh, I think someone have left maybe.
Doctor,
Yeah.
can we talk privately just for about a minute, for 1 minute after the lecture?
Okay. So 11, maybe 1 or 2 more students. Okay, I stop recording, sorry.